Hello and welcome to Linear Algebra, Section 3.4, Composition and Inverse of a Linear Mapping. Let's look at composition and inverse. You probably remember from college algebra how to compose functions, but we find with a linear mapping, if the two maps being composed are linear mappings, then the composition is also a linear mapping. So let's look at theorem 4.1. Says the following: let U, V, and W be vector spaces over field K. If F and G are linear mappings, U to V and V to W, then the composition map, G composed with F, is a linear mapping. And you see the proof of that theorem. It's just a matter of taking two vectors, U and V, in U, and working with the linearity of both F and G, along with scalars, and you eventually get that the composition is a linear mapping. Very easy to see. I don't feel like talking through all of it, but you can see how it flows very easily. So compositions of linear mappings is again a linear mapping. So look at the next theorem, theorem 4.2. This theorem tells us that compositions are distributive over addition, and scalars can go in and out wherever. So if U, V, and W are vector spaces, and then F goes from U to V and G and H go from V to W, then G plus H composed with F is G composed with F plus H composed with F. And the same thing for scalars. Scalars can go in and out wherever, and if T is from U to V, then you have the right-hand side distribution. G composed with F plus T is G composed with F plus G composed with T. So, and now we notice that, suppose next that if U and V and W are all three the same vector space, and F and G are two linear mappings from U to U, then in general, F composed with G may not be equal to G composed with F. You see examples of that in college algebra, for example. But let's look at the following example where the compositions in opposite directions are not the same thing. Suppose U is R3, and suppose F is the linear map from R3 to R3, given by mapping the ordered triple XYZ to XY0. And let G be the map from R3 to R3, mapping the ordered triple XYZ to the ordered triple XZ0. Now F and G are very similar, but G is slightly different to F because you're swapping the Y for the Z. Now G composed with F is G of F of XYZ, which is G of XY0, but how does G operate? We see that G will always have 0 in the third component, and it has the z in the second component. And so g of x, y, 0 is what? X, 0, 0. F composed with g is f of x, z, 0, which is x, z, 0. And they're not the same. G composed with f is not the same as f composed with g. Now, if you look at a linear mapping f going from v into v, in other words, the domain, codomain are the same, that's called an operator, a linear operator. And you can use the power notation for f composed with itself n times, for example. F to the nth power is f composed with f composed with f composed with f n times. And if r and s are non-negative integers, then f to the r plus s power equals f to the r power composed with f to the s power. And we'll use that from time to time. Now let's look at Theorem 4.3. Theorem 4.3 tells us the following. If f is a linear mapping from u to v, and suppose that f has an inverse, g, from v to u, then the inverse, g, is a linear map. Now, when the inverse exists, the inverse is also a linear mapping. All right, so let's consider the proof of Theorem 4.3. And this is one for which you would be responsible. All right, proof. So we want to show that G is a linear mapping. So we need to start with two vectors in V. So let V1 and V2 be two vectors in V. We first must show that G of the sum, V1, V2, equals G of V1 plus G of V2. And then similarly, you would have to show scalar multiplication. Now, let's look at it. G goes from V to U. All right? So let's let U1 equal G of V1 and U2 equal G of V2. Then since F and G are inverses of each other, what does that mean? It means that F of U1 equals V1 and F of U2 equals V2. Operate by F on both sides. Now, F is a linear mapping. So F of U1 plus U2 is F of U1 plus F of U2, which equals V1 plus V2. Turn that around, okay? V1 plus V2 equal F of U1 plus U2. Now, apply the inverse G to both sides of that equation. G of V1 plus V2 equals, and then G and F cancel out, equals U1 plus U2, which equals, the way we have it defined, G of V1 plus G of V2. So we've proven the vector addition. Similarly, G of CV equals C times G of V. And that's an exercise in the homework that you'll turn in for me, exercise 3. So we know now, whenever a linear mapping has an inverse, that the inverse itself is also a linear mapping. Now, as a corollary, corollary 4.4, Let F be a linear map from U to V. Suppose the kernel of F is trivial and F is surjective, that is, onto. Then F has an inverse linear map. Proof is simple. Since the kernel's trivial, we know that F is injective, or one-to-one, and so now what? F is bijective, and hence F has an inverse, and the inverse is linear by theorem 4.3. Remember that a linear mapping has an inverse if and only if it's bijective, one-to-one and onto. Now, look at example 1. Suppose we have the linear mapping f from R2 to R2 given by f of xy equals 3x minus y, comma, 4x plus 2y. Show f has an inverse, okay? So we show f has an inverse by showing that it's bijective. So first, we want to show it's injective by showing that its kernel is trivial. So its kernel is found by setting the mapping equal to 0, 0, the 0 vector of R2. So we have two equations that have a linear system. 3x minus y equals 0 and 4x plus 2y equals 0. And yes, we can use matrices with row reduction. So we take the matrix, 3, negative 1, 0, 4, 2, 0, row reduce it to reduced row echelon form, we get the identity. So that means that both x and y must be 0, hence we have shown that f is injective. And then referring to our dimension theorem, so we know the kernel is trivial, meaning it has dimension 0, and the dimension of R2 is 2, hence the dimension of the image must be 2 in order for 0 plus 2 to equal 2. So we have shown now that f is both one-to-one and onto. Hence, it has an inverse mapping. And we've already defined it, of course. A linear mapping that has an inverse, that is, bijective, is called an isomorphism. And the two vector spaces are called isomorphic vector spaces. They behave in the same way. They're not the same vector space, but they behave in the same way. And then look, if you will, at example 2 here. And this is very important because this is the converse direction to one we had last week, where we were looking at a linear mapping going from V into, I believe it was Kn at the time, and we established that there was a mapping from the basis of V to the coordinate vector in Kn. Now this example is actually going from Rn to V. So let's look at it. Example 2. Okay. Let V be a vector space having dimension n, a finite dimensional vector space. And let B be a basis, V1, V2 through V sub n. Now, I'm going to go ahead and use Kn because it works for Kn as well. Let L be the map defined from Kn to V by L mapping an ordered n-tuple, x1, x2 to xn, to the linear combination of the basis vectors of V. x1 v1 plus x2 v2 plus dot 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 plus x sub n v sub n. Then we're claiming that L is an isomorphism. Okay? And to show that it's an isomorphism, we need to see that it's one-to-one and onto. And so let's check to see if the kernel of L is trivial. Well, the kernel of L would have to be trivial, since when you take the linear combination, xi vi equals 0, all of the xi's would have to be 0 because the vi's are linearly independent, right? And the image of L is all of V, since the basis vectors span or generate V. So by corollary 4.4, L is an isomorphism. It's both one-to-one and onto. And Kn and V are isomorphic to each other. Okay? Now, just as a matter of notation, oftentimes we'll leave off the little circle when we're dealing with composition mappings and just say that Fg equals F circle G. And again, remember that in general, compositions are not commutative, right? Generally speaking, Fg is not equal to Gf. However, powers of mappings commute, like the identity mapping, which would be f to the 0 power, and then you have f to the first power, f squared, f cubed. They do commute. So this was a short lesson for this section. Homework 7 is on page 70. Exercises 3, 4, 5, and 6. 4 exercises this time. 3, 4, 5, and 6. So that concludes the video for 3.4.